whatever. These are pendula in the water. And Miguel had this big idea a few years ago, and we are doing this experiment. He invited me to help them to do the experiments, but it's a super hard work. We are facing a lot of problems because we are doing experiments in the lab. Actually, this kind of structure, they work properly if they're very close to the surface, but not that close, right? So we need to check that the water level is the same at every time. And it turned out that actually we observed that we are losing a bit of water, right? And of course, we are making Stokes waves. You see that, sorry, I have to use this. But usually, if you go in the books and in the papers, you find solution for Stokes wave with a leading term, which is a negative term. So the water depth is not the water depth that you think, but it's a little bit lower. Okay, that's a solution for that. I mean, you get an equation like this, and then what you have to do is to update the water depth, but then you have to calculate all the phases, shifts, and etc., and all the coefficients. And this kind of correction are in a third order, are in the order of steepness, right? But what if we don't like to have this leading term here? We consider the Bernoulli equation, the linearized Bernoulli equation, and we add a term to the surface elevation, so the mean is 0. And we have this thing that it depends linearly on time, which is it's not a big deal, because in order to get the flow, we just need to take special derivatives, and this thing disappears always. But actually, this is a bit patchy, because these two terms, this one and this one, they come out from the canonical transformation, and then they are son of the same mathematical operation. So we have a current, and we don't know how to remove the current, because the current is a problem, actually, because in order to construct the Zakharov framework, we started from this assumption, no flow condition at the boundaries. And if we have a current, the current is not 0, very far away. And actually, if you take a Stokes wave, probably you should not allow a Stokes drift too. So where's the problem? Where's the kind of mistake? The mistake is that we are calling for Dirac deltas of the Fourier transformation. Our wave number space is continuous. The Fourier transform allows Dirac deltas, so sinusoidal waves in space, but sinusoidals are not 0, very far away. So we have this problem of this misunderstanding. And these misunderstandings create the singularities at that we are some singularities here and there in the canonical transformation and that current. So start from scratch, and if you read the Zakharov seminar paper, he shows that this thing, this Hamiltonian, generates these two variation equations that are corresponding to the first two equation of the water wave problem, the dynamic and kinematic condition on the surface. Of course, you have to add to the Hamiltonian problem the Laplace equation and the bottom boundary condition. But that problem on the right is not solvable, actually. There's something missing. Anyone has a guess? What's missing? What's missing? What's missing? Actually, in order to... Oh? Yeah, of course. Thank you. In order for this thing to be equal to that thing, Zakharov uses the Green theorem and requires that this integral is 0. It's the flux of the potential. I don't know what it does mean, but you needed to close it's a requirement for the boundary condition. So actually, if this integrand is 0, no flow condition, the integral is 0. You can guess, we can think about a huge number of other boundary conditions. Probably we can take a tank, which is of this, made in this way. We put a wave maker here, rigid boundaries, an absorber here. As far as we conserve this quantity, we have a correspondence from the original water wave problem, and we can use the Hamiltonian framework. Now I will just do the things for a square box, like Miguel says today, and what comes in on one side goes out on the other side, exactly the same. This is the periodic boundary condition, and it makes this integral 0. Okay, so these are the Fourier modes. I don't write the summation sign because then we have to write a lot of summation, but these things are the physical variables expressed in Fourier modes, are the inverse transform for the quantities, the potential at the free surface, and the surface elevation. If we do all the calculation that Miguel told you this morning, we get to this very compact form of the total energy, which is exact. There is no approximation here. This is a result of the Taylor expansion close to the free surface, and we have all the nonlinearities. Lambda here is a set of wave numbers. So zeta with lambda here is a product over all the wave numbers, and here we have a huge number of summation that I'm hiding. But I did put this thing because it's because I found that this general coefficient here has a general form. Of course, you need to compute all the coefficients. Krasinski computed the first 4 or 5 coefficients, and this corresponds to the Krasinski coefficients. But the nice thing is that if m or n is equal to 0, which corresponds in my ordering, but you can order in a different way, put 7, multiplies psi 0, and sorry, if m on n or n is equal to 0, it corresponds to the coefficient that multiplies the potential 0, the mean potential. It turns out that these coefficients are all, for any order of nonlinearity, are 0. Okay? This means that if you take, according to this equation, if you take the derivative of the total energy where the potential, the mean potential is not there, you get this law here. The mean water level is a constant. Of course, you can do it with Leibniz rule from the free surface equation, but this is a reassuring thing, right? On the other hand, we are, if we account for zeta 0, and we want to solve this equation for m equal to 0, so we want to see the evolution of the mean potential, we see that we have a zeta here, right? So we at least have g. If we do this derivative, we have g zeta 0. So in general, this guy is not a constant. It is a constant in deep water, but not in intermediate waters. This is what creates all the misunderstandings. But what is something that is constant in space and changes in time? Bernoulli constant. Okay. This is not, a few weeks ago I thought we were speaking with Miguel about that, and I thought that this was just something varying, and of course if you take the derivative in space of this thing, that gives you the velocities, the derivative is 0, so it's not important. But if you want to compute wave energy fluxes, radiation stress, and all this kind of stuff, this is something that you have to take care about. Well, we have to take care about, not you, everyone. So, summarizing. Fourier transform, we solve the equation for the free surface elevation, and guess what? We say for the mean free surface, and we say that, okay, we keep the 0 value as initial value, so we have this reassuring thing that when we remove an average from the measurement, we don't have to mess it up with the different mean water level, right? And then we introduce the canonical variable, which in my notation is alpha, not A or B. So you're getting the same equation with different flavors today, which is nice. And then, well, the total expansion is in compact form because Miguel today already showed you the first term. So this is just a picture, a drawing, just to say that we have a canonical expansion. And we get to the Zakharov equation. For very specific choices of the coefficients. And I wanted to, it's interesting, it would be interesting to discuss about these choices, but I think I will stop here with the theoretical stuff. How much is it? How much time do we have? 5 minutes. Okay, just a couple of examples of how to use the canonical transformation and everything. Well, of course, the strategy in phase space is to solve this equation at any time, to evolve the variable beta, which is the reduced normal variable. But then in order to get the flow, we need to plug beta into the canonical transformation. Then we have to do this transformation for m different from 0. And we plug everything back into the inverse Fourier transform, and we get the variable that we measure actually. So the surface elevation, you can write it in a compact form too. And for a single harmonic, Levi-Civita showed that this thing converge. Maybe there are some mathematicians that in some other cases tells you that it converges. But I wrote this in compact form just to tell you one simple thing, that at any level, if you put m equal to 0 here, it means that we are computing a mode corresponding to k0. But this coefficient have a general form. Since we are skipping in the summation the wave number 0, the average of this thing is 0. And by the way, the second order coefficient are exactly Schaumendin and Dalzell, and the long bound modes are the one given by Loget-Higgins, etc., etc. So everything is in place. What about the fluxes? This exercise to compute the mass flux or the momentum as a connection to what we were talking about yesterday. In order to do this integral, of course, the phi there is a hyperbolic cosine, so we need to do the integral, have a hyperbolic sine, then do a Taylor expansion, and plug in all the other transformation, all the bound modes. And I want to display only the interesting second order terms, which I think are important for, it's the lowest level for this community, for wave modeling actually. Because actually these two terms comes from the fact that we are accounting for the surface elevation when we are doing the integral. The last term, which has this b, it comes from the expansion of the canonical transformation, from the canonical expansion, right? N is a vector corresponded to the wave number with the same label. Okay, so n, it means that it's the wave number n. This is an element of a square matrix. These two guys are non-zero on the diagonal. These two guys are 0 on the diagonal. If we take an expectation with a random phase approximation, at leading order, the spectrum is E with the Dirac delta, like Miguel showed this morning. And we find that the expected mass flux in a certain volume is just the energy divided, the sum of the energy divided by the phase celerity. That is the integral of the Stokes drift. There's no other long wave contribution at this level. So the return flow probably comes out from one of these members. The return flow that we were talking of McIntyre, we were talking about yesterday. So that's it. So basically, first point is don't mess it up with the wave zero number, because it tells you about mass conservation and the forces. And actually, it gives a contribution on the stresses. Yeah, and as Miguel showed told this morning, the periodic system is a little bit more intelligible for human beings like us to describe the things. In the tank there was a leak, so probably that was the problem. And don't mess it up with number 0. Yeah, that's it.
Oh, that's